This is, as you see in the picture here, in the middle of the picture here. If I can make it bigger, I don't know if I can make it bigger, but I can. But here is the setup here of determination of the molar mass of carbon dioxide gas. Carbon dioxide gas, the theoretical molar mass, which is the literature one, is 44.1 gram, 44.0 gram per mole. Now today we'll do the experiment. I need two students. One will help from this side to take the whole closer to the camera so the camera can see it. I need two volunteers here to hold the whole setup, so in the future the students will see it. Two volunteers. Yeah, come and volunteer. Take the whole thing up. Yeah. Slide. Slide. It's heavy. Up, down. No, from the base. Yeah. Take it from the base. Yeah. So take it up a little bit so it can be seen.
Pick it up?
Yeah, up a little bit. Yeah. And yeah, it will not fall. So this is the setup here. You can see as we have a main flask. One is generating the carbon dioxide gas between HCl and the calcium carbonate, and one is collecting flask. This is generating flask for CO2. This is collecting flask for CO2 gas. Thank you very much. That's all. Thank you. Now we can go back and look at the procedure and everything of this experiment. Thank you very much. Because if you have not done this, this is very important to have this structure here. Now I can tell you up front here, we can see some sources, a lot of sources of error inside this experiment, and somebody can tell me where are those sources of errors might be. We have two flasks. Let me just go to the iCollege, and I want to go to iCollege and then look at the iCollege here, and look at the procedure, at the whole thing, at the diagram of this experiment. And as you will see, a lot of points where the sources of error might appear. Or we might have some sources of error in the past, and even with this, because this setup is putting a lot of stuff open. So one of the source of error is the equipment, your equipment where you generate your CO2. It has to be clean and dry. It has to be clean and dry. So if you have impurities, you will add the impurities to the mass of gram per mole, correct? To the mass of carbon dioxide. So let me go for us. Here it is. I'm just looking at the I put for you a lot of questions for the lecture and the lab review for the final exam. The final exam is in the lab, and the lecture is ACS type of exam. So be prepared of it, so we can, if we have time permits, we can have what they call it, we can have a review, correct? So we can have a review. So I'll take the PDF file here. So this is the PDF file. I'm interested, first of all, the generation of CO2 here is, I think you did this experiment in the maybe before, or chemical of reaction here. So it is here. We are generating carbon dioxide here, gas, and we are collecting it. So we are generating it and we are collecting it, correct? So, and the measure of the STP, standard temperature and pressure, we determine its molar mass. Molar mass. So this is the whole idea, is to get the molar mass of CO2. Now the theoretical value is around 44 gram per mole. And then you will do your percentage error. You will see how close you are from this value, or how far you are from this value. Now, if you are too much of far off, then you have to put a reasoning inside discussion why your value is far off from the accepted literature value, which is 44.0 gram, around that value. So we will have a calcium carbonate with will come like a chip, marble chips, or like white chalks. Remember the white chalks all times. And then you'll put HCl on it, and then you'll generate CO2. You collect CO2 gas, and then you will display the CO2 gas with H2O, correct? You measure the mass of H2O, which will be the same mass of whatever. I mean, we determine the mass, and then you divide it by the density of H2O to get the volume of H2O, which is what? The volume of CO2. From there, you can combine. Here it is. So let me take this one here. First of all, you collect CO2, okay, over H2O, and then you determine the mass of H2O, then the volume of H2O. Okay, the volume of H2O will be volume of the gas, and then we'll be using this one here as STB combined. We'll use combined gas law. So you have STP, standard temperature, and pressure. At the STP, standard temperature is 0 degrees Fahrenheit or 32 0 degrees Celsius or 32 Fahrenheit, or we'll be using just Kelvin, 273.15 Kelvin. So it's 32 Fahrenheit, 0 degrees, or 273.15 Kelvin. We'll be using the Kelvin. That's the standard temperature. The standard pressure is 1 atmospheric pressure, 1 ATM. We'll not use the SI Pascal, we'll use 1 ATM. Now, those are the conditions we are using at STP. We want to get this one here, the molar mass of CO2 at STP. Now we measured everything at what? At the lab condition. The lab condition we have, you will measure the temperature of the lab. Just take a thermometer from drawer, put it in the bench, and measure the temperature. And the pressure, I have to locate the manometer in the, I don't see any manometer, but it's close to one. We are very close to Savannah to sea level. So at Savannah sea level we have 1 ATM, but this one is very close enough. So this temperature here will be, as what it says inside the procedure, around 21 degrees Celsius. You will add to it 273.15 to convert it into Kelvin. This is the local one. This is the local condition we did our experiment in, correct? But we need to get the molar mass at STP. So this is STP. That's a combined. This is the pressure here. You'll measure, I think it's 0.98 something, close to 1. I don't see any manometer, but I'll look into it. If there is no manometer here, then we'll be using whatever the procedure says, the values, 0.98, 0.99. We are very close to Savannah area, so 4 hours is not far away, so we are at the sea level, close to sea level. So it should be close to 1 ATM, correct? Now from this, having those two conditions, one at STB we want to collect, and one at the local condition, at the lab condition. So we'll have the combined gas law. It is, somebody remembers the combined gas law? Remember that? We're not yet there, but this is PV1 T1 equal PV2 T2 and T1. Sorry. T1 and this is T2. Now whatever is, we are looking at the STB. If this is local lab conditions, and this is STP condition, correct? And we want to get the volume of CO2 in what? In STP condition. So if we get the volume, then it's very easy to get what the molar mass, correct? So that's what we are looking for. That's the whole thing here. Local condition, so we have manometer, we can measure this. Temperature is around 21 degrees Celsius converts to Kelvin. The V1, this is from the experiment, and this one we don't know. This one is 1 atmosphere at STP. This one here is 273.15 Kelvin. This one here is about 21 degrees Celsius. You convert it into Kelvin, add to this one here into Kelvin value. And this one here is, if we don't have manometer, we'll be using theirs. I think it's ATM, close to 1 ATM. So with the whole idea to get the V2. Now let me go and look at the I'll take this one out. Everybody has it? Everybody has this? Who's that? Okay, that's fine. That's fine. Go ahead. Whatever you find. Okay, so let me take this one out. So you are generating CO2, and then you're collecting CO2 over H2O. You assume that's the volume of any gas is the volume of what? The container. So CO2 will take the volume of the small flask here you have. So we'll fill it with H2O. The volume of H2O will be equal to the volume of the gas itself. Now, this is the setup here. You'll be generating this is the calcium carbonate. You put your HCl here. The HCl, you'll have a solution. You have to make a solution, 15 ml concentrated acid of HCl plus 15 ml distilled H2O. You'll fill then the graduate cylinder up to 100 ml with the tower after that. So this is just the ratio between them, and then you put the diluted acid inside, and then you generate CO2 over. This is calcium chloride. Calcium chloride is used to what? Used to any moisture will used to take any moisture out. It's really a very good adsorbent. Correct? So then the CO2 will come here. CO2 will be generated, go in. Okay guys, and then you let it fill for 20 minutes first, generating, so you drive all the air out. Air should be out. Okay guys? So, and then after that, you'll generate this one another 10 minutes just to make sure that's your weighing of this, because you have to take it. But before you start, that's the source of error. You have to make sure this connection here is really dry. So you'll take we have an oven there, or put it in 70 degrees. You will take this flask here, okay, with this tubing here up to here, so up to this tubing here. So this tubing here, this part here, take it, you rinse it with acetone and put it at least for 15 minutes inside the oven, just to make sure that's everything pure and dry. That's the first thing is, and this is the major source of error. If you just have a problem with this and you did not give it a time and you did not rinse this one here very well with acetone, you might have impurities and you might have still any moisture of H2O still there, correct? So that's what the first step is, to make sure that your setup here, this is a collecting, that's what we are collecting. This is called collecting container, or Erlenmeyer collecting container, or Erlenmeyer. Okay, we are collecting CO2 inside. This one here we are generating or producing container. We are producing CO2 here. Okay, guys, and we'll do it twice, one 20 minutes, other time 10 minutes. Now the weighing, when we add all the CO2 is out, we'll come and fill the whole thing. We have to, the whole setup has to be weighed with the tubing. Tube here and tube here, up to here. Not that this stuff, but from here. It has to be weighed first empty. After you are drying it from acetone, get it from the oven, keep it cool a little bit, and then don't touch it with your anytime with your what? Don't touch it with your hands. After the oven, no more at your hands. Anytime to use it, you have to use tissues to carry out this from the balance. So weigh it empty after you are come out from the oven, and then when you have this 20 minutes and 20 minutes, and then take it and weigh it, CO2. Then do another 10 minutes, weigh it. The weighing should be close to each other, not 0.00003 zeros. No, that's that's impossible. You can get this one here. And then we have another issue. We have to fill this one here full all the way to the top with distilled H2O. I'll not use tab, or to be consistent, because you added here distilled. You will add distilled H2O here. You fill it all the way to the top, and then you weigh it. You cannot weigh it in the small balance. You have to put flat balance. This will be very heavy. When you fill this one's Erlenmeyer flask all the way with the two tubings, distilled H2O, and then weigh it, that will be a larger amount. So, and then you get the weighing. Okay, so the weighing should be really consistent. The weighing should be really consistent. So, and really you will do all this here, and then we'll come back to the here tell you are generating it's and that's this value here. Don't consider it, because this is very hard to utilize. I can tell you up front, so don't waste your time. You'll be here until maybe the second day. You will not get this one here in the lab unless you have a very good precise analytical balances they give you to this. But anyway, so you have to get this here. At least the reading had to be, when you collect this here, the reading has to be really really close to each other, very close to each other. So then you have the room temperature is given to you. You can measure, get your thermometer to measure the room temperature. Manometer, I don't see any manometer here. If we have, then it will be close to 1 atmospheric pressure, 0.99, 0.98, something like this. Otherwise, we'll be using, if we don't have manometer, we can use theirs, whatever is given here to us. Where is it here? In the here, guys, look at this. We'll be using those values here. Can you see the values here? You can use those values here. These are the B2 and the T2, or those are STP temperatures, correct? Those are STP temperatures. This is here, as I mentioned for you, this one here, this is a combined gas law, and this one here, STB conditions, and this is local lab condition. So now I understand we might not have the condition here, so they use the P1 is this one here, the local 0.982. You can use it as is. Please use this one here. If we don't have the manometer here, I can show you actually to read it. It's very simple, but I don't see it. So, but anyway, so if we don't here, but this temperature you can measure it. You just put your thermometer on your desk on the bench for a couple minutes, 10 minutes, and then read whatever in Celsius, and then convert it into Kelvin. Correct, guys? So you will collect the first one here, the mass gas collection and air. You will weigh this one here. Let me we got this one here. Yes. Yes. The two tubes, you take, maybe I have to put here, look, those two tubes here, this one here, don't take the drying agent. You see the drying agent there? It has a, can you see the drying agent from here? This is the first tubing here, and this is the second one. So here it is. Okay, guys. In one of the step of the process, you have to make sure that there are no air inside. Correct. So you can use the vacuum. Well, I can. We'll check if the vacuum's working, because a couple of weeks ago the vacuum's not working. So you warm it a little bit up, the flask itself, with the tubing. Always this cut. This is one. That's tubing number one. Go in all the way. This is going out. You can use this one here in the vacuum itself, or you can use this one here when you heat it up a little bit to vacuum. Use it for the vacuum, or just keep the CO2 will go out, the air will go out, and then you will get the CO2 will go out. Okay, guys, those are the two tubings. This one here, up to here. Of course, this is the lid here. Up to here is the tubing one, and up to here, the second tubing. Can you see it? Can somebody show her where the tubings are? Don't take the adsorbent calcium chloride. Somebody can show her the whole thing. How does it look like? I might Google that to show you, so the picture is not maybe clear, but all the time you treat this one here from this side, guys. You cut it off from this side. This is the one you are working with. This one is, you don't touch this. This setup is just put calcium carbonate in it, small amount, 0.3 to maybe 5, 6 gram, half a gram there, and then put HCl, diluted HCl inside. You dilute HCl inside, and then you generate. But this one is not touched. Keep it as is, correct? That's why you have to put it in and out. This one, the one have to wait in and out and put it back in. Are you following me here? So the idea is to replace the air with H2O and the H2O mass, and then you transfer it into volume of the H2O, which is then our perception that the CO2 volume is the volume of the container, which is the volume of H2O. And that's what the assumption is, which is really correct. The volume of H2O will equal the volume of CO2, because gases, they don't have real shape. Their shape and volume. Their volume and shape is the shape of the container itself. Correct, guys? Now let's look at the calculations here. The whole thing is straightforward. There's nothing really mysterious about this. But there is coming in and out, taking this one in and out. There's always possibility that air might come in. Luckily enough that CO2 density is heavier than air, so the air will not push CO2. Cool yourself down now. Cool yourself down. So the air is lighter than density-wise than CO2. But if you keep the for a long time, for some reason, talking to your partner, and then keep your flask here, well, the air will be able, because the airflow here with the hoods will be getting your CO2 out, and that's a major error. Are you following me here? That's a major error, another error. Weighing, another error too. So therefore, you have to be consistent at least to get the two readings very close to each other. Okay, guys. So I want to go through calculation to show you here with how we do the calculations here. Now, the gas collection flask and H2O. That's when you 20 minutes for carbon dioxide, let it purge the whole air inside. You get what? You get the flask and the CO2 gas. You take the CO2 gas out, you fill it then with distilled H2O. I prefer using distilled H2O than the tab H2O. Then you weigh the collection flask with H2O, correct? And this is mass of the collection flask and air. That's the beginning of the whole thing. That's when you take it out of the oven, after drying it, after cooling it. That's when you started with, correct? So the difference between the steps will give you the mass of H2O inside the collection flask. I have the mass of collection flask. I can use the density of H2O is 1 gram. So I get the volume of H2O, which is equal to the volume of what? Of the gas. The gas takes the volume of. So in the step, this one here, I get the volume of H2O and the volume of the gas itself, correct? At room temperature and the pressure. So those room temperature, as I said, use theirs. That's local conditions here. Right here, please write a note for you. Those values here, this value here and this value here, local condition. Because we know that STP is 1 atmospheric pressure for pressure and 273.15 Kelvin for temperature. That's the star. So the barometric pressure, we don't have barometer, but if we don't have it, look at this. If we have it, I'll show you how to read it. It's easy. It's not really difficult. You just look at the meniscus of the mercury there. From the bottom of the meniscus, you can determine how many centimeter, which is read in centimeter or millimeter mercury. So each centimeter is what? 10 millimeter. Each centimeter, 1 centimeter is 10 millimeters, correct? So then the room temperature, you can measure the room temperature. That's local condition. Local, right there, local condition. Okay, so it said 21, so it's given to you the local one. The STB given to you, this is STB here, right? This one here, STB. This is local. So from there, I can get the V2 at STB, correct? Now, we have to get the mass of the dry air at flask at STB. Density of the air is given to you. The density of the air is given to you. Here it is. Multiplied by the volume. The volume is in step 7. This volume here, V2. This is V2 here. Correct? And then mass of the whole empty flask when you are rinsing it with drying acetone. Let me just take this one here. So this one we get the volume of is CO2 at STB. Mass of dry air in the flask at STB, correct? So we did this one here together, correct? We used the mass of the air at the flask, number step 8. Mass of empty flask, that's after rinsing it with acetone, correct? After rinsing it with acetone. So I will not, it says rinse the whole tubing, but I hope it's not taking that much time of drying the tubing there. The glass will dry quickly, but the tubing might not. But it says inside the procedure you might have to use dry even the acetone with it. So I would rather not do the acetone inside the tubing. It might take more time than 15 minutes to dry those tubing. Acetone will not attack the tubing. The tubing is non-polar plastic, and acetone is polar. So the acetone is not dissolving those tubing. So then you have several weighing after needed to get the closer masses, correct? Then mass of CO2, step 10 minus step 9, and then here 12 is mass of CO2 from step 11, volume of from step 11 x 22.4 liter. It says that's 1 mole of a gas. That's what Avogadro said. 1 mole of a gas will give you what? 22.4 liter of that gas as a volume. Each 1 mole of a gas will give you 22.4 liter of that what they call it, of that gas. And then the accepted value here is 44. The accepted is 44 gram. So we are using it like this one here. Accepted value means literature value. Accepted value is literature value, which is this is, so the experimental value, this is 40.0 minus your value, okay guys, divided by 40.0 multiplied by 100%, multiplied by 100. That will give an error. So after you finish, come and tell me how your error. So if you get larger error, that means the drying, the beginning of the drying, and then in between you talk maybe with your partner a little bit, you forgot to you don't let the CO2 just escape, and then you get air inside the system, correct? So I think that's really all. And then when you are done, we'll dump out the HCl with the whole thing in, not in the sink. We have here a container for the waste, okay? If you have a solid, leftover solid calcium carbonate, we'll not throw it in the sink, we'll not throw it in this here. Add more HCl to it to get rid of it, correct? CO2 will come as calcium chloride and CO2 and H2O. So that's, you can dump in the sink, but don't dump leftover crystals of calcium carbonate, of marble chips. No. Just kill all those calcium carbonate by adding more HCl in a beaker, and then you can rinse the whole thing together. So I think that's all. It's straightforward experiment, but it has a lot of error, sources of error everywhere. Weighing, drying, correct, waiting time, and that's the reason you have to use more than one purging of CO2. 20 minutes first, and then 10 minutes, and if the weighing is not, add another 10 minutes, and so on. Okay guys, so that's about it, and let's start.